let's do some triple integrals in cylindrical coordinates. Cylindrical coordinates. So essentially, cylindrical coordinates are polar coordinates plus z coordinates. So cylindrical coordinates are r, theta, and z. So the transformation, the relation between cylindrical and rectangular, x equals to r cos theta and y equals to r sin theta. This is in polar, and then z is z. So this is the transformation. If we know the cylindrical coordinates, these are the formulas for the rectangular coordinates. Right. So also the volume element is important. Let's try to figure out intuitively what's the volume element. So think about an infinitesimal cylinder like this. So let's imagine that the base of the cylinder is dA, and dA pertains to the xy part, in which we use polar coordinates. So dA in polar coordinates is r dr d theta. And the height of this infinitesimal cylinder will be dz. Now the volume of the cylinder is area of the basis times height. So the volume of this is dv is r dr d theta dz. In practical problems, we can permute as needed dr d theta dz depending on the order of the integrals. Okay, so let's try to let's start with a very simple problem. What about, let's rediscover the wheel just to get our hands tried first. So let's see, what's the volume of the cylinder? So the cylinder is, let's call it T, x squared plus y squared less than or equal to r squared, and z is between 0 and h. Okay, so what is the volume of this cylinder? It's triple integral over E, like every, the triple integral of the dV is the volume of the solid E, right? So this is a triple integral. Okay, let's see, let's express the cylinder in cylindrical coordinates. A small r, the meaning of the small r is the distance from a point in the 3D to the z-axis, right? So that's a cylinder. It's a cylinder with axis of symmetry z-axis. And then the variable r is between 0 and capital R. So small r as a cylindrical coordinate is a distance to the z-axis. So again, very important. Small r equals to distance to the z-axis. So small r is between, let's put here, small r is between 0 and the radius of the cylinder. So small r is between 0 and capital R. Theta is between 0 and 2 pi. Again, what's theta in this context? Theta is the rotational angle around the z-axis, right? So can I put, so let's put all of them here. So r is the distance to the z-axis. Theta is the rotational angle around the z-axis. Okay, so because the cylinder is centered around with the z-axis axis of symmetry is rotationally symmetric, theta is between 0 and 2 pi, and z is the height of the cylinder is is from 0 to h. Right? Okay, so let's see what is this integral. Triple integral over e r dr d theta dz. Okay, so this is a triple integral of a separable function. So that's a separable function. So in that it splits into a product of a component which is in terms of r only times a component which is in terms of z only times a component which is in terms of theta only. So this one, and this one. So now let's apply the 3D version of separable over rectangles. And so r, this will be r integral from 0 to capital R, small r, dr. Theta integral from 0 to 2 pi of d theta, done with this. And z integral from 0 to h of dz. And this will be capital R squared over 2 times 2 pi times h, simplified to the 2. So we rediscover the wheel, so to say. So that's pi r squared h, area of the basis times height. Just to see, just to start with slightly more complicated problems, so see this works. Okay, so let's try to go to the next problem. Okay, so let's consider the following solid. So this solid E is within a cylinder. So x squared plus y squared less than or equal to 1. So let's so much about x and the y, and then z is between 0 and the upper part is a sphere. So the upper part is square root of 4 minus x squared minus y squared. So is within a cylinder between the 0 plane and a sphere. Right? It's between the xy plane and a sphere center at the origin with radius 2. So this being said, we need to find the triple integral over e of the function z times square root of x squared plus y squared dv. Okay, so let's see how can we set up this integral. So again, in cylindrical coordinates, x squared plus y squared equals to r squared. Always keep this in mind. More r squared. So actually, what we really want to integrate is triple integral over e of z small r, and dv is r dr d theta dz. But we have to see what to integrate first. So in this case, because z is between 0 and this kind of not so nice formula, it would be nice if we have a square at this side to cancel the radical. So we integrate z first. So from 0 to square root of 4 minus r squared. Then we integrate r second from 0 to 1, because this is r squared is from 0 to 1, and this r is from 0 to 1. And then we integrate theta, which means theta is, again, these are rotationally symmetric solid from 0 to pi. So these are the limits of integration. Let's see, we integrate r squared z, right, dz dr d theta. Okay, so let's integrate. We move from inside out. Let's integrate the variable first. So integral from 0 to pi, integral from 0 to 1, r squared z squared over 2 from z equals to 0 to z equals to square root of 4 minus r squared. Right. And then we integrate dr d theta. Theta is last. So this will be, let's put 1 over 2 in front of the integral, because from here, so we get integral from 0 to pi, integral from 0 to 1. Okay, when z is 0 is 0. So what matters here when z equals to square root of 4 minus r squared is r squared times 4 minus r squared dr and then d theta. Right. So this will be 1 over 2 integral from 0 to pi 4r squared minus r to the power 4. The angle derivative is 4 over 3 r cubed minus r to the power 5 over 5 between r equals to 0 and r equals to 1, and then d theta. That will be 1 over 2 integral from 0 to pi. Let's put it here. What's 4 over 3 minus 1 over 5 is 17 over 15. 17 over 15. D theta. This will be 17, so 1 over 2 and 17 over 15 times 2 pi. That will be, the answer is 17 over 15 pi. Okay, so the third problem we do is a problem which is useful to physics and engineering, basically. But before, let's try to say a few words about inertia moments. So we have a solid the z-axis as a solid in 3D. Straight here. A solid in 3D. This comes with a local density function, rho of x, y, z, where the dimension of the of rho is kilograms meters to the power minus 3. Kilograms per cubic meters. So rho of x, y, z is the local density. So in other words, rho of x, y, z, if you multiply local density, so the density around the point x, y, z with the volume element dv, we'll get a volume times density is the mass. But what mass? The mass of a tiny grain of matter around the point x, y, z. So this will be dm. Okay, so we get a concept of inertia moment I sub z is a triple integral over the solid t, x squared plus y squared, which is the distance, again, r squared. The cylindrical coordinates r squared, which is the distance to the z-axis, the square of the distance to the z-axis, in here, dm. Right. So that's the definition of the inertia moment of a solid with local density of x, y, z, and we respect the z-axis, right? So to simplify one further is triple integral over e, then put just r squared dm, where r is one of the cylindrical coordinates. or if you want to expand with until the variable, so I sub z is the triple integral over e x squared plus y squared times rho of xyz times dv. So this will be the formula in terms of the x, y, and z of the inertia moment of the solid E, this E here. This whole thing is E. So I sub z is triple integral over this solid E, x squared plus y squared, that means the square of the distance to the z-axis, times dm, which is rho of x, y, z, dv. So it's like the discrete form will be the sum of the mass times the square of the distance to the z-axis. And we sum all the masses for all the particles in the solid. Right. Okay, so let's apply this principle, this formula, to calculate the inertial moment of a uniform cylinder of mass m and radius r with respect to its axis of symmetry. So let's see. In this case, we got our regular cylinder, this one, x, y, and z. This is a cylinder with radius r, and the density is rho 0. Let's say this rho of x, y, z equals to rho sub 0 equals constant. So this cylinder is a solid cylinder with constant density. And the radius is r, and the height is h. So how to express this cylinder in cylindrical coordinates? So we have small r is between 0 and big R. Now, being rotationally symmetric, theta is between 0 and 2 pi. And then z is between 0 and h. First of all, because we need to express the inertial moment in terms of the mass, let's find the formula for the mass first. Mass of this uniform cylinder is the density rho 0 times the volume, but the volume of cylinder is pi r squared h. So this is to be kept in mind for later. So that's the mass of the cylinder, density times the volume of the cylinder. Okay, so now let's start to calculate the inertial moment of this solid cylinder with respect to its axis of symmetry. So I sub z is a triple integral over E, being E, the solid cylinder being E, triple over E, r squared times rho 0 times dv. Let's put rho 0 in front of the integral. So it's rho 0 times the triple integral over E r squared dv. And that will be rho 0 times triple integral over E r squared times r dr d theta dz. This being the volume element in cylindrical coordinates. But look at the description of the cylinder in cylindrical coordinates. It's a box. It's a box in cylindrical coordinates. So let's apply now the separable of a rectangle 3D version. Okay, so it's rho 0. So that's separable. The r part, the theta part, the z part. And over every variable between two numerical values. Right? So by using separable over rectangles, it's r integral from 0 to big R, small r cubed dr times the theta integral from 0 to 2 pi of d theta times the z integral, which will be integral from 0 to h of dz. Okay, so I sub z turns out to be rho 0 r the power 4 over 4, capital R the power 4 over 4 times 2 pi, let's say the integral is 2 pi, times capital H, H is the third integral. So simplify a 2 with a 4 here, I got a 2 at the bottom. So is rho 0 times pi r the power 4 h over 2. So that's the formula for the inertia, moment of inertia of the solid cylinder with respect to its axis of symmetry. But let's try to connect it with the mass. So let's erase the work and keep the root of the work. I sub z turns out to be this one. So it's rho 0 pi r the power 4 h over 2. Okay, so let's out of this rho 0 pi r the power 4 h over 2 decouple rho 0 pi r squared h. So let's decouple this amount from I sub z is rho 0 pi r squared h. And then what's left to get here? We need an extra r the power 2 and over 2, right? This, why did we decouple this? We decouple the mass. So this will be the mass of the appearing in the inertial moment, and m r squared over 2. So we got a very neat formula. I sub z, the inertial moment of a solid cylinder with uniform density of mass m with respect to its axis of symmetry is 1 over 2 times the mass of the cylinder times the square of the radius.